All right, let's dive into one of those super powerful but kind of behind-the-scenes techniques in deep learning. We're talking about batch normalization. It's this awesome trick that basically helps our giant neural networks train way faster and, honestly, just perform a whole lot better. So, you know how deep learning models are behind all these incredible AI breakthroughs, right? Well, getting them to actually work is a whole other ballgame. Seriously, training these massive networks can be a total nightmare. It's often super slow, things can go wrong all the time, and they're ridiculously sensitive to how you first set them up. We're talking about a huge bottleneck that can literally bring progress to a grinding halt.
But what if there was one simple, kind of elegant technique that could just fix a lot of that? Something that could dramatically speed up training, make the whole process more stable, and boost performance, all with just one simple addition to the network? Well, that's exactly the promise of batch normalization.
Okay, so to really get why this is such a game changer, we've got to understand the problem it's built to solve. Let's dig into that deep learning challenge.
All right, let's cook up a super simple example. Imagine a neural network with just two inputs. We'll call the first one x1, and let's say its values range from 0 to 1. Pretty standard stuff.
Okay, now here's the catch. The second input, we'll call it x2, has a way smaller range, like from 0 to just 0.01. So think about that. One input is on a scale that's literally 100 times larger than the other.
And that, right there, is a massive problem. This kind of imbalance makes the learning process completely erratic. The network just struggles to adjust its weights. It's like it's trying to listen to a whisper and a shout at the same time. It can't properly tune into both these tiny changes and these huge changes simultaneously.
So how do we fix this? Well, the first step is a really classic technique in data science. It brings us to what we can call the normalization fix.
The basic idea here is something called normalization. It's basically just the process of taking all your data and squishing or stretching it so it all lives on the same scale. A super common way to do this is to make everything fit neatly between -1 and 1.
And by putting all the inputs on a level playing field, we're helping the network learn so much more effectively. It doesn't have to fight with those mismatched scales anymore, and that helps it generalize way better. Now, this is a really crucial first step, but it only fixes the problem at the front door. The issue actually goes much deeper inside the network.
And this is where the real magic happens. This is where we leap from a simple fix to a truly revolutionary technique. So let's talk about batch normalization.
So the brilliant insight, which came from some researchers at Google, was basically asking this one powerful question. They said, okay, normalizing the inputs is great, but what if we didn't just do it once at the start? What if we kept normalizing the data, resetting it to a stable, predictable state between every single layer of the network? And the concept is just beautifully simple when you see it. Instead of the data just flowing straight from one layer to the next, we just stick a batch norm layer right in between them. Think of it like a little regulator. It's an extra step that recenters and rescales the data as it goes along, stopping things from spiraling out of control. And the effect of this one tiny change? It's absolutely profound. It acts like a governor on an engine, just smoothing out that chaotic learning process. And the result? The network learns so much faster. It becomes way less picky about how you set it up initially, which, let me tell you, saves a ton of time on tedious tuning. And the whole training process just becomes way more stable and reliable.
Okay, so you're probably wondering what's actually happening under the hood here. Like, what's the technical reason this is so darn effective? Let's break down exactly why it works.
All right, the key technical term here is something called internal covariate shift. It sounds complicated, but the idea is actually pretty intuitive. As a network learns, the weights in every layer are changing all the time, right? Well, that means the output from one layer is also constantly changing what it looks like. This creates a moving target for the next layer in line. I love this analogy. Imagine you're trying to shoot an arrow at a target, but the target is just erratically jumping all over the place. That's what each layer in the network is dealing with. Batch normalization basically just anchors that target in place, which dramatically reduces this chaotic shift and gives each layer a stable foundation to learn from.
And the key thing to remember is that this isn't a one-and-done fix at the beginning. No, we apply this normalization process over and over, all the way through the network. So, after each hidden layer does its thing, a batch norm layer steps in, stabilizes the output, and then passes it along to the next layer.
So what this all boils down to is that by normalizing the activations from each layer,
Batch normalization makes sure that every single part of the network is getting inputs that are consistent and predictable. And that stability, that's really the secret sauce that makes the whole learning process so much more efficient and robust. Now, if you've spent any time working with neural nets, a little bell might be ringing in your head right now. You might be thinking, hang on, isn't this kind of like dropout? And you know what? That's a fantastic question, so it's really important to get the difference. Let's put batch norm and dropout head to head.
The biggest difference between them is their main job. Batch normalization is, first and foremost, an optimization tool. Its whole goal is to make training smoother and faster. Dropout, on the other hand, is all about regularization. Its job is to stop the model from just memorizing the training data, what we call overfitting, and it does that by randomly switching off neurons during training.
But here's a really cool little detail. Because batch normalization does its calculations on small batches of data at a time, it actually introduces a tiny bit of noise into the network. And that subtle noise? It acts as a weak form of regularization, helping to prevent overfitting. So while its main gig is optimization, you get this super useful anti-overfitting effect as a kind of free bonus. Pretty neat, right?
Okay, so let's wrap this up. What are the key things you absolutely need to remember about batch normalization? First, it's a massive accelerator. It makes training deep networks way faster. Second, it's a stabilizer, smoothing out the whole learning process. And it does all this by tackling that core problem we talked about, internal covariate shift. And honestly, these benefits are so huge that batch norm has become a totally standard, must-have tool in pretty much all modern deep learning.
And that really brings us to a final thought. Batch normalization is one of those brilliant, almost invisible little tricks that make modern AI even possible. It's not flashy, but it's essential. And it kind of makes you wonder, right? What other simple but incredibly powerful ideas are hiding just beneath the surface, quietly pushing the entire field of AI forward?